Let's take a look at 8.3, which is on page 16, dealing with laws of logarithms. We're going to apply the laws of logarithms to simplify expressions. We're basically learning some rules for logarithms that will make our work with logarithms simpler. It's kind of like you have rules for exponents or powers, so that you add exponents when you multiply, or you subtract exponents when you divide, or you multiply exponents when you have a power of a power. We have these rules of how to handle exponents. Well, we have rules for logarithms as well. So, as I've just said, just as there are laws of exponents, there are corresponding laws of logarithms. There's only three. There's the change of base formula as well, but there's really only three. There's what we call the product law, the quotient law, and the power law. And I'm going to talk about these one by one, but the first thing I want you to note is I see in your package, it's not a correction, it's a thing that we should probably get in the habit of doing. You should have brackets around that m to the n. Okay. I mean, when you have, we can talk about something we just did in one of the examples. When we have log base a of a to the 0.8, you don't need brackets around the a to the 0.8. It's implied that it's a to the 0.8, and then you take the logarithm of it. Bless you. But I would like you to get in the habit of putting that set of brackets. Okay? If it's a single thing for an argument, if it's log base 2 of 16, there's no need to put brackets around that argument. But if the argument is a power, if the argument, which is the thing you're taking the logarithm of, is a base raised to an exponent, I think it's a good idea to put those brackets there. Okay? So let's go through these first of all. The product law. The product says the logarithm of a product is the sum of the logarithms. Now, just a second here. I've been trying to teach you that logarithms are exponents. And when you multiply powers, you add the exponents. Well, that's kind of why we take log of m plus log of n. And it's also the reason why you can use a slide rule to multiply numbers, because you take the two rulers and you slide one to a certain location, and you can find the difference between the two locations, or the sum of the two locations, depending on which way you slide it. So we're just going to try this, and I'm going to go with my calculator in the mode that I don't like it to be in, which is math print. It's the mode that most of you are in. This, of course, allows me to use the log base function in a sensible way. You can still use it, but you have to put a comma, and there's syntax involved. So log base 5 of, and I'm just going to put 220 here. I don't need to type 220. I could have typed 20 times 11. But that's what 20 times 11 is. And I get this. What this rule says is that that's supposed to be equal to log base 5 of 20 plus log base 5 of 11. I have no earthly idea why I have brackets around the 11 there. They're not needed. So I'm going to have log base 5 of 20 plus, it would be nice if this function had its own key just on the main part of the calculator. Log base 5 of 11. See, that's one thing I don't like about this. It starts pushing stuff off the screen. But you get the same result. Okay, so I did it up here. I did it using a change of base formula, which if you don't have the log base function on your calculator, there's one or two of you that don't, then you have to use the change of base formula. But they're equal. This says, and I'm not going to go through and do this, this says that if you had log base 4, for example, of 82 over 3, that's the same as log base 4 of 82 minus log base 4 of 3. And you can convince yourself of that. But I want to point something out to you before we go on. Does the order in which you add these two logarithms together, is that going to affect the result you get? No. Does the order in which you subtract these two It does, doesn't it? Subtraction is an order-sensitive mathematical operation. And what that means is you have to remember that you take the logarithm of the numerator and then you subtract the logarithm of the denominator. You can't just, as my mom would say, willy-nilly just subtract some logarithms. They have to be in a certain order. And I always say this, and it isn't intentional. I always say, this is the most powerful rule. And then I go, oh, it's the power rule. It's no pun intended. It is a powerful rule. It is something that is very, very important. Those of you taking calculus, don't confuse what this rule is with differentiating polynomial terms where you move the exponent down in front. It's something different. Okay? This rule says when you take the logarithm of a power, you are allowed to instead take the logarithm of the base and then multiply by the exponent. Okay? So let's try that. Let's take log base 8 of 7 raised to the 3. Whoops, just happened there. Log base 8 of 7 raised to the 3. We get that number. Instead, let's take 3 multiplied by log base 8 of 7, and you get the same thing. And you might say to yourself, well, why can't I just do it the first way? I'll give you a very basic example here of a question that might appear on an exam. You're asked for the value of that. Well, if I take 8 to the 325, I want to figure out what 8 to the 325 is. I get an error because my calculator can only handle numbers up to 9.99999 times 10 to the 99. So if you tried to put this into your calculator, I'm going to go under an assumption here that if we went log base 2 of 8 raised to the 325, I'm going under the assumption that your calculator is going to calculate that 8 to the 325 first and then take the logarithm of it. But it can't, because that number's too big. That's what overflow means. It's going past its memory. However, we can go 325 times log base 2 of 8. And you should know that this is 3. So good numerical response question. What's it equal to? 975, because 325 times 3 gives you 975, I think. Yeah. So those are the 3 rules. And what we're going to be spending the class doing is going through a variety of different things that you need to know how to do. One of the things you're expected to be able to do is to take a logarithm of an entire term, and I'm going to rewrite it with the x squared y in brackets, but again, it doesn't have to be, and write it as a bunch of logarithms added or subtracted together. Well, since x squared times y is a product, this is log base 3 of x squared plus log base 3 of y. And then I can move that 2 out in front. Because the question says write each expression in terms of logarithms of x and logarithms of y, not logarithms of x squared. So this 2 is an exponent, and the power law says I can do this. I think everybody is going to graduate to a point, maybe you're already here right now, where going from here to here is just done. You're going to separate these pieces out, and you're going to move the exponents down in front where they turn into coefficients. That being said, how many of you can appreciate that this will become that? It's a quotient, and the logarithm of a quotient is the difference of the logarithms. By the way, again, notice how everything's lined up. The x, the log, and the z are all on the main line. The 6's are subscripts, and then that exponent of a 3 is a superscript. That 3 can go out in front now, where I can write 3 log base 6 of z. I want to point something out to you, that because this variable is in the denominator, the logarithm is negative. Okay? I want to point that out to you. It's looking at the quotient rule in a slightly different way. If there's an argument or a part of the argument that's in the denominator, the logarithm that goes with that argument or part of the argument will be negative. Okay? Log base 2 of xy cubed over z squared. Again, if you want, it's not entirely necessary, but it might be a good idea later. We can put brackets around that. Well, that will be log base 2 of the numerator minus log base 2 of the denominator of the original argument. But then, this is log base 2 of x plus log base 2 of y squared minus log base 2 of z squared. Y cubed, not y squared. My mistake. Are you okay to that point? By a show of hands, wait till I write it down and turn around to see if you put your hand up. By a show of hands, I'm interested in knowing how many of you would have simply said log base 2 of x plus 3 log base 2 of y minus 2 log base 2 of z. That's kind of the goal. This is pretty simple so far. You don't really need to think about it too much. The x and the y cubed are in the numerator, so their logarithms are positive. The z squared was in the denominator, so the corresponding logarithm is negative. D, log base b of that beast. I'll tell you what the biggest mistake is. People look at this and they go, well, it's going to be log base b of x to the 4, and I can move that 4 in front. And then I'm going to subtract for the denominator. The denominator is going to be a log base b of y to the 10, but I can move that 10 in front. And there's a product here, so I need to add the base b logarithm of z cubed, and I can move the 3 here. What's wrong with that picture? Kai?
It's still a denominator. So.
Right, so there's two ways to approach this. The z is in the denominator, so if you want to go with my little rule, this is minus, right? Is there another way, without using the rule, it's going to be like one of these internet problems, that I can make 2 marks on this to make it true, keeping the plus? Right, brackets. But as things get more complicated in these types of questions, putting the brackets may seem a little unwieldy. Of course, these are both going to become negative. And if you want to trace, we'll get to the final answer in a second, but if you want to trace from the question down to this, it's log base b of x to the 4 minus log base b of y to the 10 z cubed. But this is this. And I hope you appreciate that I'm sure you do. Even though these rules are new to you today, those two things should be like hello and bonjour, right? I mean, they're the same thing. So I don't even feel the need to explain that I'm moving the 4 down every time I do something like that. Anyway, what you do get is 4 log base b of x minus 10 log base b of y minus 3 log base b of z. Any questions with that one? Just curious is all. How many of you are comfortable in just kind of taking that leap? Okay, and you do need to know something here, that a base, I'll use b for base, taken as a root, nth root, is that base raised to the reciprocal of the index of the root. So a cube root is equivalent to taking that base and raising it, or that radicand, I guess, and raising it to the third, which means this is log base 7 of x to the third minus, because we're dividing in the argument, minus log base 7 of y to the half. Okay, so you swing the exponents down and we're done. It's not difficult. What might be challenging for some people is there's all these rules that we have to apply, plus we still have to be aware of our exponent laws. We're still going to be using those. Use laws of logarithms to simplify and evaluate. We are not throwing this into our calculator. Again, I ask this question because it helps me as a teacher, and I'm also asking to challenge you. How many of you see that that's equal to 3? That's equal to 3. Because log base 2 of 40 minus log base 2 of 5 is log base 2 of 40 over 5, which is 8. This is log base 2 of 8. And everybody should know that log base 2 of 8 is the exponent to which you raise 2 to get 8. We're kind of back in the same arena that we've been in before, which is, if I say to you that you can simplify this and figure it out without a calculator, then change its appearance. Combine the two logarithms into one and see what happens. Here, this is going to be log base 3 of 45 times 15 over 25. I know, and I already saw a few of you grab your calculator, but we could simplify some of this. I'm really not a fan of seeing this on an exam. But we can. I think it just gets messy. I divided 45 by 5 to get 9, 25 by 5 to get 5. I can then further divide this 5 and this 15 to get 3. And all I'm left with in here is 27. This is log base 3 of 27, which is 3. And I'm just doing it that way to, force my hand and get you to think a bit, rather than just always going to your calculator. Oh, while we're at it, I'm going to go back here and just show you something. Remember this question? This, what we're trying to find, is log base a of b minus log base a of c. It's 4.5 minus 3.7. Didn't have to think about it at all. Didn't have to think about converting from logarithmic to exponential. The answer is right there. And had this been that, it would be that. You'd take 3 times 4.5 and subtract 2 times 3.7. C. Well, let's simplify this. This is ooh, I was going to say it's all log base 8s, but it's not. Let's remove those brackets first of all. This is log base 8 of 48 plus log base 8 of 4 minus log base 8 of 15 plus log base 5 of 5. And let's leave aside for the moment.
We have a log 8 instead of a log 5.
You have a log 8 instead of log 5? Okay. Do you see that we still could have done it with a log 5, log base 5? Because log base 5 of 5 is 1. Okay. But yours is an 8. Okay. Good to know. I will have to change that. These are all log base 8s. So we can pack them all together. Notice I got rid of the brackets, and I did this intentionally. It's so that my new argument is going to contain numbers on the top that come from the positive logarithms and numbers on the bottom that come from the negative. The only negative logarithm is the log base 8 of 15. This is not a negative logarithm. It's not a negative logarithm because it's minus that logarithm. It's a positive logarithm. So I'm going to have on the top 48 times 4 times 5. 5 over 15 is 1 over 3. 3 goes into 48 16 times. I think this is 64, but you'd want to check it on your calculator. I think the argument works out to 64. It does. Thank you, Thomas. So we get log base 8 of 64. Wow, that's like stealing candy from a baby. The baby's even asleep, right? 8 squared is 64, so log base 8 of 64 is 2. These are all log base 21, so we can pack them together. It will be 7 times 9 times a third. 9 times a third is 3. 3 times 7 is 21. So it's 1. These are not questions you would get on an exam because you could just put them in your calculator. Incidentally, I don't know if you remember this, but I told you yesterday, I gave you a couple of rules that aren't on your formula sheet. One of them was that if you want to take a logarithm of 1 over something, you can flip that over and just make the logarithm negative. That should make sense now. Because 1/3 is 3 to the negative 1. 1/3 is 3 to the negative 1. I can move that negative in front and just write 3. In which case that 3 would go on the bottom. You'd have 7 times 9 over 3, which is the same result. Well, I can't figure out what these are, but if I put them together, I get log of 5 squared plus log of 20 squared. So I can't figure out what each one is, but now I get log of 5 squared times 20 squared. So sometimes we want to pack them back into a single log, including exponents. Of course, this is base 10. Is that 10,000? Is that what that works out to? Thank you. So this is log base 10 of 10,000, which is 4. And never think, just because you could have done it on your calculator, that's all you need to worry about. Anything that can be done solely on the calculator, I can turn into a question that cannot be done on a calculator. But we're starting off with numbers because it's easier. How many of you, when you take a look at f, immediately see that it's 0? There are a number of ways to do it. There are at least 3 ways to do it. By a show of hands, how many of you said that this is 3 log x minus 3 log x? But how many of you did that? How many of you said, and that's 0 obviously, how many of you said this is log of x cubed minus log of x cubed? Anybody? Yeah. Fewer, but still possible. How many of you went so far as to say this is log of x cubed over x cubed? Probably nobody. But it is, isn't it? And x cubed over x cubed is 1. And log base 10 of 1 is the number to which you raise 10 to get 1, 0. It's all self-consistent. No matter which path you take, you're going to end up at your destination, as long as you follow the rules. Number 3, write each expression as a single logarithm. I would really hope, I don't even know that we need to write anything here other than xz over y. The biggest mistake is seeing log y plus log z and thinking you're going to multiply the y and the z together and put them on the bottom. If it were this, these are base 10 logarithms, then it would be log of x over yz. But it's not. That log of z is a positive logarithm, so it goes on the top. The z goes on the top. Over here, well, these are all log base 2s. Log base 2, let's see, I've got a positive, and 2 negatives of x times 2x over x squared times y. I get an x squared on the top and an x squared on the bottom. And now we start to see cracks in the nice shiny veneer of easy questions. Okay? Because on a multiple choice question or a numerical response question, you might be told that this is equal to 1 minus log base 2 of y. And maybe that's a multiple choice. Maybe it's a minus log base b of y, which, I mean, it's got to be b is 2, but you have to figure out what a is. How many of you know how to go from log base 2 of 2 over y to 1 minus log base 2 of y? What would I do, Thomas? Right. And it's a minor thing, but we wouldn't say log base 2 to the 2. We would say log base 2 of 2. Yeah. Definitely. This is log base 2 of the numerator minus log base 2 of the denominator. And just to finish off that thought, Thomas, what's log base 2 of 2? It's 1. It's the exponent to which you raise 2 to get 2. I'm not sure why anybody would do this. But this happens to be true as well. Because really, I can think of this as log base 2 of 2 times 1 over y, can't I? There's other ways to wrap your head around it. So it's log base 2 of 2 plus log base 2 of 1 over y. So we could write it in that form. All right. 2 more quick questions here. I think we're kind of winding down here. This will be log base 10. It's a base 10 logarithm of, I'm going to have x cubed root y. Because the y is going to carry an exponent of a half as that coefficient goes up to the top, which is the power law in reverse. We'll have y to the half, and that happens to be the square root of y. Again, base 10 logarithms. We don't need to write base 10. It's going to be a on the top, a plus b on the top, a minus b on the bottom. And that's it. But I'm finishing with this example to try to keep us grounded in our rules in algebra. Why? Why am I not allowed to do something like that?
Because A is not a factor on the bottom.
Right. A is not a factor on the bottom. If it were a factor on the bottom, how would it present itself? What would it look like?
A times negative.
Right. It would be A times something. It would be A in brackets. So because it's A minus something, all bets are off. So you can't do anything with that. That's it. Those are the laws of logarithms. These are on your formula sheet, by the way. Just take a quick peek at your formula sheet. We've got a couple more minutes here. We're kind of getting down to it on the formula sheet. Is there anything we haven't learned yet? No, there's some stuff here. Ooh. Ugh. Some stuff we're going to learn in the very final unit dealing with combinations, permutations, and the binomial theorem. But that's it. So we've got our exponential growth and decay formula at the bottom of the screen here, which we've learned about. We have the change of base formula, which I talked about yesterday. You don't need it. Sometimes it's useful. What the curriculum says is if teachers want to use the change of base formula to teach students how to calculate logarithms, they can, but they don't have to, which tells me it's not a big deal. And then the three rules for the laws of logarithms are above that. So we're getting very close here to the end. The next unit, by the way, is just a real heavy algebra unit. There's some other issues that we're going to deal with. And then the final unit is something totally different. Page 31 of the handout, 1 to 6, 10 to 17.